Hi, welcome back to another exciting Math 112 lecture. We are going to today talk about section 8.2, which is all about polar coordinates. Now, don't get yourself all worked up and worried about polar coordinates. It's just another way. Sorry, my computer's misbehaving. It's just polar coordinates are just another way that we depict coordinates in space. Up until now, we've been living in the Cartesian coordinate system. In the Cartesian coordinate system, we move along an XY grid, a rectangular grid. Sometimes it's more convenient to live in a circular space. And that's what polar coordinates do. Polar coordinates define points in space in terms of a radius and an angle of inclination rather than an x and a y. The radius, or r, gives us the size of the circle, meaning how far out from the origin is our point. And so we go out a certain number of units, so from our origin, we go out a certain number, a certain distance, but then our angle theta tells us that we're going to rotate that distance at some angle of inclination, and that is where we put our point. So let's take a look at this. So we're going to plot these 3 points on this polar coordinate system. And I will give you this image in a printable form on the course website so that you can have it. While I'm thinking about it, also on the course website, we're going to look at Desmos and to do some of our graphing. And in the module for this chapter, so if we go back to the course homepage, and we look at the module for chapter 8. You may or may not have ever done this before, and yours might look a little different because I've got some extra stuff because I'm in the teacher view. But right here is where section 8.2 begins, and if you click here on polar coordinates on Desmos, this will take you to a page where you can then open up the Desmos graph that is all set up to help you with polar coordinates. And we'll be working with this in a minute. But for right now, we're going to figure out how to graph these by hand here. So the blue circles represent our radius values. And so this guy here is going to be 1. This guy here will be 2, 3, 4, and 5. And the numbers out here give us our angles of inclination. So the point 3, 5 pi over 3, remember 3 is my radius, 5 pi over 3 is my angle of inclination. So 3 puts me on this circle, and then I go out to 5 pi over 3, which is clear down here. That is my point A. B is on my radius 2 circle at an inclination of pi over 4 right here. So that's point B. C is clear out here at my 5 at 7 pi over 4, which is down here. Okay? No real magic. We can do the same thing in Desmos. So let me turn off this. So all of these blues, all of these blue guys, Those are what make our grid for our window over here. All right, sorry, whoops. Here we get two fighting mices, and I just switched to win. There we go. Okay. So my first point was three. So we'll just graph the point. Whoops, not there. Go down one. 3, comma, 5 pi over 3. And Desmos, yes, it's right here. So you can see this blue ray gives us the 5 pi over 3. That doesn't look right. Okay, so be careful on this one. The points aren't going to work out quite right because the points are based on the XY coordinate system. So don't try to do this for points, just use it for curves. We'll come back to that. Okay, sorry about that. My system is really disliked. I made some changes to my settings. I may have to figure out what I did. Okay, so this all looks okay. If you have any questions with graphing polar coordinates, think about it and bring them to a study session. And let's go on here. So we can convert between Cartesian coordinates and Cartesian coordinates and polar coordinates. And we do that using these relationships right here, which are all based on our old friend, the triangle that we can inscribe inside a circle centered at the origin. We've seen this before. This is how we defined our trigonometric relationships to begin with. Now we're just realizing that, oh, well, if I'm going to talk about how a point moves around a circle, I can talk about this in terms of the radius of the circle and the angle of inclination. And these are our basic relations. So let's practice. Let's convert the point r theta, which is 3, 3 pi over 2, from polar coordinates into Cartesian coordinates. Okay, so we know that x is equal to r cosine theta. So that's going to be equal to 3 times the cosine of 3 pi over 2. We remember that the cosine of 3 pi over 2 is 0, so this is 0. And y is r sine theta, which is 3 times the sine of 3 pi over 2. Sine of 3 pi over 2 is -1, so this is -3. And in Cartesian coordinates, 3, 3 pi over 2 corresponds to 0, -3. Let's see how Desmos handles this. So let's put on the point. Zero, -3. And sure enough, now we can see that, so this point went right here, and we can see that the point in Cartesian coordinates 0, -3 corresponds to a radius of 1, 2, 3, and an angle from the x-axis that is pi and a half, or 3 pi over 2. All right. So on this graph, that is the same one that I linked for you, if you just enter points, Desmos is going to read those as XY coordinate points. Okay. All right. So now let's go the other way. Let's go from Cartesian to polar. So we remember that x squared plus y squared equals r squared, which means that r is going to be, we can just worry about the positive one, the principal square root of x squared plus y squared, or -3 squared plus -4 squared, which is going to give us 5. So we know my radius is 5. Now all we have to do is get to theta, and we can get there a couple of ways. We know that x over r is equal to cosine of theta. So -3 over 5 equals cosine theta. Remember from previous work that that means that we can take the inverse cosine, and we find theta equals 2.2214. And remember, this is going to be radians. You can do this in degrees as well, but we typically do this in radians. But remember also, by symmetry, there's another angle that has cosine of -3/5, and that's going to be 4.069 radians. My original point, -3, -4, is going to be down in the third quadrant, so we want the third quadrant version, so we'll use this one. So my r theta will be 5, 4.069 radians. Okay. So we can also sketch curves in polar coordinates, just like we can sketch lines and curves in Cartesian coordinates. And the basic form, so remember in Cartesian coordinates, if you have a y equals 3, that's a horizontal line. If you have x equals 4, that's a vertical line, right? The most basic form we can make in polar coordinates is a circle. So if we have got the equation r equals 2, that just means that that is a circle with radius 2. No matter what theta is, every point on this circle will satisfy the equation r equals 2. In Desmos, we can just type r equals 2. Let me make this one be something other than blue so we can see it. Red's a good choice. And here we go, r equals 2. It is behind my other line, but you can see it there. let me play with this for a second. Let me make these dotted so that this shows up better. There we go. If I put this one there, now it's on top. Okay. So let's see what else we can do. Let me erase my ink mark here. And let's look at r equals theta over pi. So we're going to make a table of values here, just like we would if we were doing this in Cartesian coordinates and weren't sure what shape we were going to get. So r theta. We're going to let's pick a theta. If theta is 0, that means r is 0. So we'll have a point here at 0, 0. If theta is pi, that means r is 1. So at pi, I have a point that is 1. So let's get some points in between. If theta is pi over 4, that means r is 1/4. It's going to be, this is 1, so 1/4 is about here. At pi over 2, we're going to have 1/2. At pi, we're already to 1. If theta is If theta is 5 pi over 4, that means my radius is 5/4. So 1 1/4. At 3 pi over 2, my radius is, wait. Sorry. I screwed that up. We know we've got a point at 0, 0. If theta is pi over 4, my radius is 1/4, which is clear down in here. If theta is pi over 2, my radius is 1/2. If theta is pi, my radius is 1. If theta is 5 pi over 4, my radius is 1 1/4. At 3 pi over 2, radius is 1 1/2. At 2 pi, radius is 2. You can see what we're getting here. We are going to get a spiral. It's going to look like this. I can't draw it very well. Let's see how Desmos does. You just type theta over 2. Turn it back on. And there is our spiral. This is one of the powerful things about Cartesian coordinates. That spiral curve would be a royal pain in the neck to describe in Cartesian coordinates. But in polar coordinates, it's a very simple curve. And we see that quite a bit, actually, when we start looking at polar coordinates, we find that curves, particularly circular curves, that would be very difficult to describe in Cartesian coordinates, turn out to be pretty simple relationships in polar coordinates. So let's go back here to our PowerPoint. And let's just do this again. We're going to sketch r equals 5 sine theta. This is where your knowledge of the unit circle comes in handy, right? Because you can make a theta r table. You know that when theta is 0, the radius is going to be, what's the sign of 0? 0. So we've got a point at 0, 0. If theta is pi over 2, the sine of pi over 2 is 1, so your radius is going to be 5. At pi, sine, you're going to be back at 0. Well, this is going to be interesting. We go from 0, 0 to 5. I guess we're going to have to get some points in the middle. You get the idea. Let's let Desmos do this. So radius equals 5 sine theta. And again, we get a circle. Now, remember that, so this is a circle that is offset from the origin. This is actually, so play with this a little bit and understand how things get shifted, because it's a little bit different. So if I just type in radius equals 5, I get a circle centered around the origin. But when I say radius equals 5 sine theta, I get a circle of radius 5, but it's no longer centered at the origin. It is centered, it is shifted vertically. Let's see what happens if we say r equals 5 cosine theta. That gives us a shift horizontally. The 5 still gives us the magnitude of the radius of the circle. But whatever we apply to theta gives us a vertical or horizontal shift. It's kind of fun. Okay. Now, let's do this one. Let's do r equals 6 cosine theta plus 3. I'm going to just put this on Desmos because it's going to be a little bit hard for me to draw. So let's use Desmos here. You could sketch this by hand by simply plotting points on your polar coordinate paper. R equals 6 cosine plus 3. 6 cosine theta. We know that this part would just give us a circle. But what happens when I add 3? Ooh, I get an inner loop. Wow. Well, that's interesting. So let's look at this a little bit. So what happens? Okay, well, if theta is 0, I guess we are going to sketch this because this is interesting. This thing actually has a name. Its name is a limacon, and it's a circle with an inner loop. It's like if you took a rubber band and twisted it and turned the inner part inside. So let's make a table. Theta r. So if theta is 0, cosine of 0 is 1 times 6 is 6 plus 3 is 9. 1, 2, 3, 4, 5, 6, 7. I can't even graph that. That'd be clear over here somewhere. Okay, so let's try theta is pi over 3. If theta is pi over 3, the cosine of pi over 3 is 1/2. 6 times 1/2 is 3. That is 6. So 1, 2, 3, 4, 5, 6. So already I know I've come from here into here. Let's see what happens at pi over 2. The cosine of pi over 2 is 0. So now I'm into 3. 1, 2, 3. Okay. Two pi over 3. Cosine of 2 pi over 3 is negative 1/2. So 6 times negative 1/2 is negative 3 plus 3 is 0. So 2 pi over 3, my radius is 0. Oh, here we go. Here's how we get that inner loop. Okay. So I have 2 pi over 3. I'm being a little picky because I want angles with nice cosines. So let's try pi. At pi, my radius is negative 3. Okay, so this is a little weird. Normally we go this way to make radius, but when it's negative, instead of coming out towards our angle, we go the other way. So this would be 1, 2, 3. So we got this. Okay. And now we're going to get, so we're going to go back around and come back out and get our actual shape. So it is the angles whose cosines are negative that give us this inner loop. I know that might be a little confusing. If it's really bothering you, come to one of the study sessions or make an appointment to meet with me and we will get together. Okay. So let's just do these on Desmos and take a look at what these different shapes give us. Okay. So the first one is R equals sine 2 theta. What do we think? Sine theta gives us a circle. What happens when I put a 2 in there? Oh, hey, that's kind of cool. That's called a rose. And if we were to graph out the points, we would see how this works. But it has to do with changing. Remember that when we did the sine 2 theta, that means we change the amplitude. Okay. Of our circle. Sorry, something's not looking right here. Okay. So the second one, so we got a four leaf rose. Let's look at the next one, which is R equals sine 3 theta. So make my 2 a 3, and we get a 3 leaf rose. Okay, what if R is 4 sine 4 theta? We get an 8 leaf rose. 5 theta, 5 leaf rose. So because of symmetry, even numbers, you get twice as many, we can think of as petals, as your internal multiplier. Odd numbers, you just get that number of petals. Okay, these are all called roses. Let's take a look at a couple of lemicons. We already looked at one. We looked at 3 sine theta plus 3. Well, that's not exactly the one we looked at, but so that is a type of a lemicon. Let's look at 3 sine theta plus 1. And there's the one that we saw before. Okay. Let's go back to our presentation. We are almost done. I know this one's long. I just want to do a couple of exercises with you where we transform equations from polar to Cartesian and vice versa. So we have here a Cartesian coordinate, or a Cartesian equation. And if we were to put that into our Desmos graph, you should recognize this as a circle. So let's put this in, turn this one off for a minute. And we're going to put in x squared plus y squared equals 3x. And we get a shifted circle. If we had put that in standard form, we would have been able to figure this out. But this is a circle centered at the point 1.5 at 0 with a radius of 1.5. We could put that in standard form for a circle and get that into the form that would tell us this. But what I want to do instead is write this as a polar equation. So in other words, in terms of r theta. And we're going to use the same relations we used earlier. We know that x squared plus y squared equals r squared. And we know that x equals r cosine theta. So let's just substitute those in. And we get r squared equals 3r cosine theta. This is a quadratic equation, so we're going to pull everything to the left-hand side because we want to solve for r. So r squared minus 3r cosine theta equals 0. Factor out the r. We get r times r minus 3 cosine theta equals 0. And either r equals 0 or r equals 3 cosine theta. This one, this r equals 0, that's just a point. That's not very interesting. So we're going to toss that one out. And this will be our polar form of that same equation. Let's check our work by going to Desmos. We've already put the Cartesian equation on there. Now let's put on the polar form that we came up with and see if we agree. 3 cosine theta. Turn it on. And sure enough, I only have one visible circle. They're lying right on top of one another. So we did that one right. Okay, let's do one more. We want to this time go from polar to Cartesian. So let's look at what this is. This is r equals, 2 sine theta. So 2 sine theta. Okay. We can see what this is. We know then that we're going to look for a circle. But let's go ahead and do the algebra. So r equals 2 sine theta. we're going to use those same relations that we used before. We know that x squared plus y squared equals r squared. And we know that sine theta equals y over r. So let's make this substitution first. And we get r equals 2 times sine theta, but sine theta is y over r. Let's multiply through by r, and we get r squared equals 2y. Substitute in x squared plus y squared equals 2y. If we gathered all of our variables together and completed the square on the left-hand side, we could write that in the standard form for our circle and see that that is x squared plus y minus 1 squared equals 1, which would be a circle centered at the point 0, 1 with radius equal to 1, which is what we saw on our graph. But let's go ahead and check ourselves. And we can check ourselves with the simple form. So we'll use x squared plus y squared equals 2y. We've almost got that here, 2y. And sure enough, we got it right. All right, that is all for this section. I will see you all soon, I hope, in a study session or in class. And I'll talk to you soon. In the meantime, have a great day and do good math.